This is lesson 14 in our Calculus 1 series, Related Rates. In this lesson, we are applying derivatives to application problems, and these problems are called related rate problems because we recognize that when quantities are related, their rates of change are also related. So for example, the radius and volume of a sphere are related in an equation, and so their rates of change would also be related. So let's take a look at this example. A spherical balloon is deflating at a rate of 20 cubic centimeters per second. At what rate is the radius of the balloon decreasing when the radius is 5 centimeters? So they're talking about a rate of change of the volume of the balloon, and they're asking about the rate of change of the radius of the balloon. So the first thing that we want to do in a related rate problem is to sketch if we can. So here we're talking about a sphere, so let's sketch a sphere. And step 2 is assign a variable to any quantity that is changing with time. Now we know that the radius is changing with time and the volume is changing with time. So let's identify the radius and we'll call that r. And we'll let v be the volume of the sphere. Step 3 says find an equation relating the variables from step 2. So we need an equation relating r and v, the radius and volume of a sphere. Well, we know that the volume of a sphere is 4/3 pi r cubed. So here is our relationship or equation between r and v. Step 4 says take the derivative with respect to time of the equation in step 3. If we're talking about rate of change of volume and rate of change of radius, we need the derivatives here with respect to time. So we're going to have dv dt is equal to 4/3 pi, and now we need to take the derivative here, so that's 3r squared dr dt. So the two quantities we're talking about here, r and v, are changing with respect to time, and so we're looking for an equation or relationship between their rates of change. So we take the derivative with respect to time of both sides of this equation, and that gives us dv dt is equal to 4/3 pi times 3r squared dr dt. And so simplifying, we get dv dt is equal to 4 pi r squared dr dt. Step 5 says see which derivatives or rates are given in the problem and plug them in. So let's take a look at the problem again. A spherical balloon is deflating at a rate of 20 cubic centimeters per second. Now the key in figuring out which rate this is by looking at the units. Here we're given centimeters cubed. That must be volume. So this rate is dv dt. And now notice it's deflating at a rate of 20 centimeters cubed per second. So that means this value for volume is decreasing. And so this derivative is negative 20 centimeters cubed per second. So we're given that dv dt is equal to negative 20. Are we given any other rates or any other information? No, we're just asked a question after that. So that's as much as we need to plug in at this point. So we plug in the negative 20 for dv dt. And we're here, we have negative 20 equals 4 pi r squared dr dt. And we can divide by 4 if you want on both sides. We have a negative 5 equals pi r squared dr dt. Now step 6 says solve the problem by plugging in any given variable values and solving for the rate of change. So what other information do we have and what are we asked to find? It says at what rate is the radius of the balloon decreasing? They're saying find dr dt when the radius is 5 centimeters at r equals 5. So here in step 6, we're given r equals 5 and we're asked to find dr dt at r equals 5. So now let's go here. We have negative 5 equals pi times 5 squared dr dt. And now since we've already plugged in r equals 5, I'm going to put my evaluation bar here saying that this evaluation of dr dt is when r is equal to 5. So we have negative 5 is equal to 25 pi dr dt at r equals 5. And so dr dt at r equals 5 is equal to, I'm dividing both sides now by 25 pi, and so we're going to have negative 1 over 5 pi. And what are the units here? We're talking about units of radius over units of time. The radius is measured in centimeters, and time here is measured in seconds. So the rate of change that we have is negative 1 over 5 pi centimeters per second. Step 7 is to make sure we answer the question. So let's go back up and read the question again. It says, at what rate is the radius of the balloon decreasing? Notice this negative sign is indicating that the radius is decreasing. So to answer the question, at what rate is it decreasing, we don't want to include the negative sign. We want to say the radius is decreasing at a rate of 1 over 5 pi centimeters per second. Now let's take a look at another. The radius of a sphere is increasing at a rate of 4 millimeters per second. How fast is the volume increasing when the diameter is 80 millimeters? So again, we're dealing with a sphere, but this problem's a little bit different. So step 1 says make a sketch, so we do that. Step 2 says assign variables to any of the quantities that are changing with respect to time. So again, we have r for radius and v for volume. Then we have to find an equation relating those variables. We know that volume is 4/3 pi r cubed for a sphere. And we take the derivative with respect to time of both sides. So all of this is very similar to what we just did in the first problem. So we're here and we have again dv dt is equal to 4 pi r squared dr dt. Now what are we given here? We're given the radius is increasing at a rate of 4 millimeters per second. The radius is increasing, that says that the rate is positive, at 4 millimeters per second. So dr dt is equal to a positive 4 millimeters per second. So we plug that in for dr dt. And so now we have dv dt is equal to 16 pi r squared. And what other information do we have? What are we asked to find? It says how fast is the volume increasing when the diameter is 80 millimeters. So we're asked for dv dt when the diameter is 80 millimeters, but be careful, there's no place to plug a diameter in here. We have to plug radius in. So saying that d is equal to 80 millimeters is the same as saying r is equal to 40 millimeters. Remember that radius is half the diameter. So we plug in r equals 40 here, and then we solve for dv dt. So we have 25,600 pi cubic millimeters per second for dv dt. Now let's just make sure we answered the question. How fast is the volume increasing when the diameter is 80 millimeters? We want to make sure we answer that and say when the diameter is 80 millimeters, the volume is increasing at a rate of 25,600 pi cubic millimeters per second. Let's take a look at another. The length of a rectangle is increasing at a rate of 2 centimeters per second, and its width is increasing at a rate of 3 centimeters per second. When the length is 20 centimeters and the width is 10 centimeters, how fast is the perimeter increasing and how fast is the area increasing? So let's take a look at part A for the perimeter. We're going to sketch our rectangle, and we know that the length and width are both changing, so we're going to give them variable names. So L and W and P is equal to perimeter. And we want an equation involving L, W, and P, and that equation is P equals 2L plus 2W. So now we want to take the derivative with respect to time of both sides of the equation. So we have dP dt is equal to 2 dL dt plus 2 dW dt. Now we're given that the length is increasing at a rate of 2 centimeters per second, so that says dL dt is positive 2, and dW dt is a positive 3. So we plug those in, And we're here, we have dp dt is equal to 2 times 2 plus 2 times 3, that's 10, and the units here, the units for perimeter are centimeters, units for time here are seconds, so we have 10 centimeters per second. Notice that in this part of the problem, we didn't have to use what they say here when the length is 20 centimeters and the width is 10 centimeters. In fact, the perimeter is changing at a constant rate. It doesn't matter what length and width you're talking about. This perimeter is changing always at the same rate at 10 centimeters per second. So it does not matter what L and W are. dp dt is constant, always 10 centimeters per second. So to answer part A, we want to say when the length is 20 centimeters and the width is 10 centimeters, the perimeter increases at a rate of 10 centimeters per second. That answers the question for part A. For part B, we have area, so let's also say A is equal to area, and so now we need an equation between A, L, and W for the rectangle, and we have A is equal to L times W. So again, we take the derivative with respect to t of both sides, and notice here on the right-hand side we're going to have to use the product rule. So we have dA dt is equal to dL dt times W plus L times dW dt. And again, we're given dL dt is equal to 2, dW dt is equal to 3, so we plug those in, and we have dA dt is equal to 2W plus 3L. And so notice that the rate of change of area depends on the particular width and length at that time. And we're asked to find the rate of change of area when the length is equal to 20 centimeters and the width is equal to 10 centimeters. So we plug in L equals 20 and W equals 10, and we get 80 centimeters square per second. And notice the units here, we're talking about area divided by time. So the units of area here are going to be centimeters squared, and units of time still seconds. So to answer part B, we want to say when the length is equal to 20 centimeters and the width is equal to 10 centimeters, the area increases at a rate of 80 centimeters squared per second. Let's take a look at another. An airplane is flying at an altitude of 5 miles and passes directly over a radar antenna. When the plane is 10 miles from the antenna, the radar detects that the distance between the antenna and the plane is increasing at a rate of 240 miles per hour. What is the speed of the plane at that time? Okay, an airplane is flying at an altitude of 5 miles, so its height, its altitude is going to be constant, and so it's flying horizontally, and that's 5 miles above a radar antenna. When the plane is 10 miles from the antenna, in other words, when S is equal to 10, the radar detects that the distance between the antenna and the plane is increasing at a rate of 240 miles per hour. They're giving us the rate of change of this distance. We want to know the speed of the plane at that time. So we want to know the rate of change of horizontal distance, dx dt, at that time. So the first thing we do is set up this image, and we realize that this side of our triangle is going to be constant because the plane is flying at a constant altitude of 5 miles. But the horizontal distance here, x, changes, and the distance from the antenna to the plane also changes. So they get variable names, x and s. And we need an equation that relates x and s. So we recognize that this is a right triangle, and we're using the Pythagorean theorem here. X squared plus 5 squared is equal to s squared. So x squared plus 25 is equal to s squared. And we take the derivative of both sides of this equation with respect to time. So we get 2x dx dt plus 0 is equal to 2s ds dt. Now let's take a look at what we're given. When the plane is 10 miles from the antenna, in other words, when s is equal to 10, the radar detects the distance between the antenna and the plane, that's s, is increasing at a rate of 240 miles per hour. So they're saying ds dt at s equals 10 is equal to 240 miles per hour. So we're given ds dt when s equals 10 is equal to 240 miles per hour. So let's plug that in for ds dt. That's here. And we know at this time s is equal to 10. So we plug in s equals 10. But now notice, if this 5 is constant and s is equal to 10, then we should have a specific value for x at that time as well. So we need to use the original relationship between x and s to get this corresponding x value at that time. So if s is equal to 10, we can solve for x here. X is equal to positive 5 radical 3. We're talking about a positive distance here, so we're only using the positive solution here. So x is equal to 5 radical 3, and that gets plugged in for the x as well. Now, what are we asked to find? We're asked to find the speed of the plane at that time. That's going to be dx dt when s is equal to 10. We want the horizontal rate of change here, the speed of the plane at that time. So we solve for dx dt when s is equal to 10, and we get 160 radical 3 miles per hour. And if you're curious approximately what that is, it's approximately 277 miles per hour. So let's go up and read the question again and just make sure we answer it properly. What is the speed of the plane at that time? The speed of the plane is 160 radical 3 miles per hour at that time. Let's take a look at another. At noon, ship A is 100 kilometers west of ship B. Ship A is traveling east at 35 kilometers per hour, and ship B is traveling south at 10 kilometers per hour. How fast is the distance between the ships changing at 2 p.m.? Okay, at noon, we have ship A over here. It's 100 kilometers west of ship B. So at noon, we know that the distance between A and B is going to be 100 kilometers, but that distance is changing because ship A is traveling east and ship B is traveling south. So this horizontal distance here, x, we'll call it, that's changing. Also, the distance between B's starting point and B's ending point is changing, so we'll call that distance y. And we're interested in the distance between the two ships, so we'll call that distance s. And so we need a relationship between x, y, and s. And again, we're using the Pythagorean theorem here. We take the derivatives of both sides of the equation with respect to t, and we're here. And if you want to divide by a factor of 2, we're here. So we have x dx dt plus y dy dt is equal to s ds dt. And what are we given? Ship A is traveling east at 35 kilometers per hour. That tells us dx dt is negative 35 kilometers per hour. We know it's negative because this distance x is decreasing. So dx dt is equal to negative 35 kilometers per hour. We also know something about ship B. Ship B is traveling south at 10 kilometers per hour. So this distance y between ship B's original point and the current place of ship B, that distance y is going to be changing at 10 kilometers per hour. So dy dt is equal to 10 kilometers per hour. So let's plug those in. We get negative 35x plus 10y is equal to s ds dt. Now what are we asked to find? We want to know how fast the distance between the ships is changing at 2 p.m. So we want to know ds dt when time is equal to 2 p.m. We're asked for ds dt at 2 p.m. So what do we need here in order to solve for ds dt? We need the x, y, and s values at 2 p.m. So let's think about that. if X starts out to be 100 kilometers and ship A is moving east at 35 kilometers per hour, 2 hours later, ship A must have traveled 70 kilometers. That leaves X at 30 kilometers, 100 minus the 70. Ship A moves east at 35 kilometers per hour, so after 2 hours it moved 70 kilometers, and therefore X is going to be the original 100 minus 70, which is 30 kilometers. And if ship B is moving south at 10 kilometers per hour, after 2 hours it moved 20 kilometers. So this distance Y that started out at 0, really, at noon, because it's a distance between ship B's original position at noon and its current position. So Y started out at 0, and now to that we're adding 20 kilometers. So Y is equal to 20. And then using the equation between x, y, and s, we find that s is equal to 10 radical 5 kilometers. So now we can go back here and plug in our values for x, y, and s and solve for ds dt at 2 p.m. So we're plugging in our values for x, y, and s. And ds dt at 2 p.m. is negative 17 radical 5 kilometers per hour, which is approximately negative 38 kilometers per hour. Remember, the negative signifies that the distance between the ships is decreasing, and so to answer the question we'll say the distance between the ships is decreasing at a rate of 17 radical 5 kilometers per hour at 2 p.m. Let's take a look at another. Water is leaking out of an inverted conical tank, causing the height of the water to decrease by 20 centimeters per minute. The top of the tank has a diameter of 4 meters and the height is 8 meters. Find the rate at which the water is leaking, that is dV dt, when the height of the water is 1 meter. Okay, so let's make a sketch here. We have an inverted conical tank. It says the top of the tank has a diameter of 4 meters, so I'm going to put my radius here at 2 meters for the top of the tank. And the height of the tank is 8 meters. And now this is talking about the size of the tank, and so those values are fixed. The values that change, however, are the values for the height of the water, that's h, and the radius at that height. And of course the volume, v. So we need an equation involving h, r, and v. And so we have for a cone, volume is 1/3 pi r square h. And before we take the derivative with respect to t here, let's notice what will happen if we do that. We're going to get a dv dt, a dr dt, and a dh dt. But what did they give us? They gave us the rate at which the height is changing, and they asked for the rate at which the volume is changing. They didn't say anything about the rate of change of radius. That tells us that r should not be involved here. Also, they gave us information about the size of the tank, and so let's use that information about the size of the tank to get a relationship between h and r, so we can write the expression for volume completely in terms of h. So again, notice that we're given the rate of change of the height of the water, that's 20 centimeters per minute. So dH dt is given to be 20 centimeters per minute. Notice everything else is given in meters. So I'm going to write this as 0.02 meters per minute. And we're asked for dV dt when h is equal to 1. We're not asked for or given any information about dr dt. And we're given extra information for the dimensions of the tank. So we want to replace r by what it equals in terms of h. So let's take a look at these similar triangles here. The radius of the tank is 2. The height of the tank is 8 meters. The radius of the height of the water is r, and the height of the water is h. So 2 is to 8 as r is to h. And so r is equal to 2h over 8, or 1/4 h. in this situation. So our equation for volume can have 1/4 h instead of r. Now we have a relationship just involving h and v. Now we have a simplified equation for the volume of this conical section of water. And now we can take the derivative with respect to time and proceed from there. So I want you to please pause the video and continue the problem from there. Taking the derivative with respect to time on both sides, we get dv dt is equal to, the pi over 48 is a constant multiple. This 3 comes down, we get 3h squared dh dt. Simplifying, that's dv dt is equal to pi over 16 h squared dh dt. We're given dh dt is 0.02, so we plug that in. And we're asked for dv dt when h is equal to 1. So dv dt when h is equal to 1, we plug in h equals 1 here, and then we just want to simplify. So we have 0.02 over 16 pi. If we multiply by 100 top and bottom, we get 2 over 1600 pi, or pi over 800. And the units here, we're talking about volume over time. We're using meters for a distance, so volume would be meters cubed, and we're using minutes for time here. If we want to convert this into cubic centimeters per minute, we can certainly do that. Remember that 1 meter is 100 centimeters. So if you have a meter cubed here, that's 100 cubed centimeters cubed. And so simplifying, we get 1250 pi centimeters cubed per minute. So when the height of the water is 1 meter, the water is leaking at a rate of 1250 pi centimeters cubed per minute. Let's take a look at one more. Two sides of a triangle have lengths 12 meters and 15 meters. The angle between them is increasing at a rate of 0.1 radians per second. How fast is the length of the third side increasing when the angle between the sides of fixed length is pi over 3? So we have two sides of a triangle that have fixed length. One is of length 12 and one is of length 15. And this angle is changing, and so that means the length of the third side is also changing. The angle is increasing at a rate of 0.1 radians per second. So the length of this third side is going to be increasing. So we set up our picture here, and we want to label the quantities that are changing with respect to time. We've already labeled our angle theta. Let's find a nice label for this third side. We're going to call it little c, because we notice we're going to use the law of cosines on this triangle. Remember the law of cosines? It's a more generalized version of the Pythagorean theorem. You don't need to have a right triangle here, but it relates the sides of the triangles based on the angle between two of the sides. So here we have c squared is equal to a squared plus b squared minus 2ab cosine c. So little a, b, and c are the lengths of the sides, and capital C is the angle at point C. So I'm calling that angle theta, or we could call it capital C, either way. And in this notation, this would be little a, and this would be little b. It's side A is opposite angle A, side B is opposite angle B, and side C is opposite angle C. And again, the angles have capital letters, and the sides have lowercase letters. So in this case, we have c squared is equal to 12 squared plus 15 squared minus 2 times 12 times 15 cosine angle theta. And so c squared is equal to 369 minus 360 cosine theta. And that's the relationship we have between this changing angle and the length of this side of the triangle. Once we have that relationship, we want to take the derivative of it with respect to time. So we're here, we have 2c dc dt. The derivative of 369 is 0, and so we have negative 360 times the derivative of cosine theta. So that's a negative sine theta d theta dt. So the right-hand side simplifies to a positive 360 sine theta d theta dt. And we're given d theta dt to be 0.1 radians per second. So we can plug that in and simplify. So we're here. We can even divide by a factor of 2 just to simplify a little bit more. And we're asked to find the rate at which the length of the third side is changing, so that's dc dt, and they're asking for that value when the angle is pi over 3. So when theta is equal to pi over 3. So we're going to plug in theta equals pi over 3, and we're trying to solve for dc dt, but notice in order to do that we're going to need the c value for when theta is equal to pi over 3. So let's use the equation that we started with, which is c squared is equal to 369 minus 360 cosine of angle theta. And so cosine of pi over 3 is equal to 1/2, so that goes here. And we simplify and we get c squared is equal to 189, and so c is equal to a positive radical 189 or a 3 radical 21. So that goes in for c. Theta is pi over 3, and then we can solve for dc dt at theta equals pi over 3. So sine of pi over 3 is radical 3 over 2, and then we'll divide by 3 radical 21 on both sides. And here we have a 6 in the denominator and an 18 on top, so we have a 3 here. And then if we rationalize, we realize we can do some more canceling. We have a 3 here that leaves a 7 in the denominator, and then we notice a radical 3 times a radical 3 is a 3, so we have 3 radical 7 over 7. And our units here are units of distance over units of time. So in this case, that's meters per second. So we say when the angle between the fixed sides is pi over 3, the third side of the triangle is increasing at a rate of 3 radical 7 over 7 meters per second. And so with related rate problems, it's really important to go slowly through the problem and follow all the steps. And of course, practice, practice, practice. And we'll conclude our lesson on related rates here.